Hi everyone! In this video we're going to go over a couple more electrophilic aromatic substitution reactions. The first one is sulfonation of benzene. So similar to our last lecture, we're going to start with benzene, which again is a weak nucleophile. And then we need to add in an electrophile, and it has to be a good electrophile. So what we're going to use is something called fumine sulfuric acid, which sounds kind of scary. So fumine sulfuric acid is a mixture of sulfuric acid and sulfur trioxide gas. So what we're really reacting with is the sulfur trioxide gas, and if we draw the Lewis structure of sulfur trioxide, we have a sulfur atom that is double bonded to 3 oxygen atoms. Now remember, sulfur can have an expanded octet, so it is totally valid for it to have, let's see, 2, 4, 6, 8, 10, 12 electrons here. Now the reason that this is a good electrophile is if we draw our resonance structure, we can move the pi electrons over to oxygen, and oxygen will now be negatively charged and sulfur is positively charged. And so remember that we could do this for all 3 oxygens. So all 3 oxygens are sharing that negative charge, but sulfur just has that positive charge, that +1 charge. And that's what makes it a good electrophile. Additionally, sulfur is using a 3p orbital to overlap with oxygen's 2p orbital, and that overlap isn't very good, so that also contributes to sulfur being a good electrophile here. And your textbook talks about that in a little more detail. Alright, so once we react benzene with sulfur trioxide, or fumine sulfur or sulfuric acid, we end up forming the following. So we have sulfur double bonded to 2 oxygens and then singly bonded to an alcohol group. So this is actually called benzene sulfonic acid. So that proton on the oxygen is acidic. Now you could also just write this group here that I highlighted as SO3H. So if you don't want to draw the whole structure there, you can just write SO3H instead. Okay, so let's look at the mechanism for this reaction. So how do we end up with that final product? So again, we're starting with benzene, and we would write fumine sulfuric acid, but what benzene's really reacting with is that sulfur trioxide. So we'll draw that. And again, benzene is going to attack the electrophile. And when it does that with sulfur trioxide, we end up moving one of the pi, or one set of pi electrons over to an oxygen. Oh, I'm so used to drawing benzene, I forget that the intermediate doesn't have all 3 bonds there. Okay, so our intermediate, again, is called a sigma complex, or an rhenium ion. And here we'll have a positive charge on 1 carbon And on the other carbon, we've added that sulfur trioxide group. But notice one of the oxygens is negatively charged, so that will come into play a little later. Now, remember in our general mechanism for electrophilic aromatic substitution reactions, we need a base to take that proton at the top of the ring so we can reform our 3 pi bonds. All right, so remember that in our fuming sulfuric acid mixture, we did have sulfuric acid present. So the conjugate base of sulfuric acid looks like this. And that is what's going to grab that proton up above so that we can reform our aromatic benzene ring. Okay, so now let's see if I might not have given myself enough room here. All right, so now we have our sulfur group on the benzene ring, but again, that oxygen on the right is still negatively charged. Well, luckily, we have an acid present in our fuming sulfuric acid mixture. So that's sulfuric acid down below. And the negatively charged oxygen can grab onto one of the protons on sulfuric acid. All right, so now we have our final product, benzene sulfonic acid. All right, so now let's talk about our next electrophilic aromatic substitution reaction, which is nitration. So in this reaction, we start with a benzene ring, and we're going to add nitric acid and sulfuric acid. And we end up adding what's called a nitro group to the benzene ring, which is NO2. But we'll draw the full structure just so we can see what it looks like here. All right, so notice that the nitrogen is positive and one of the oxygens is negative. So because we have those 2 charges right next to each other, this is what's known as a Zwitter ion. Well, they don't have to be right next to each other, I guess. So, for instance, many amino acids are found as Zwitter ions. They have both positive and negative charges. So we talked about this a long time ago, but just to refresh your memory of what a Zwitter ion is. Now, one way that we could use this reaction is to make TNT. So let's look at that example here. So if you start with toluene, which remember has a methyl group on a benzene ring, and you add excess nitric acid and sulfuric acid here, you end up adding those nitro groups basically all the way around the ring, but they're alternating. And this is the chemical TNT, or essentially an explosive. So notice that 2 of the nitro groups added ortho to the methyl group, and 1 of the nitro groups added para to the methyl group. And you might be wondering why. Why didn't they add meta to the methyl group? And we'll talk about the reason for that later on in part 2 of chapter 18. So look forward to that. But one thing to notice too is that the carbon to nitrogen ratio here is pretty low, and that's true for most explosives. So we don't have a super high amount of carbons relative to nitrogen. They start to kind of even out. All right, so let's look at the mechanism for this reaction. All right, so we've got nitric acid to start. And this is going to react with sulfuric acid. So the oxygen next to nitrogen is going to grab a hydrogen from sulfuric acid. And this is going to create a good leaving group, which is water. Okay, so now what we can do is move pi electrons over from the negatively charged oxygen, which is going to cause the leaving group to leave. So then we end up with something called the nitronium ion. And water, of course, our leaving group. And this is going to act as our electrophile. Okay, so then we add in our benzene as usual. And benzene's going to attack the positively charged nitrogen, which will move pi electrons over to one oxygen. And then we get our intermediate here. And then we need a base that can take that proton at the top of the ring. And in this case, we can just use water as our base. And we get our final product. Nitrobenzene. All right, now there is one more reaction we can do from here. So let's say instead of a nitro group, you wanted to add an amine. So maybe you wanted to form aniline. What you can do is actually perform a reduction on that nitro group. So let's say you formed nitrobenzene, and you wanted to actually form aniline. So you wanted to turn those oxygens into hydrogens. Well, you would need a reducing agent, and the way to do that is to add either hydrochloric acid with zinc or iron. And you would actually then follow that with sodium hydroxide. So, for instance, if we put this all together, you could say, all right, I want to start with benzene and end up with NH2 on my benzene ring. So first, I'm going to add nitric acid and sulfuric acid. Second, I'm going to add, let's just pick zinc and hydrochloric acid, but you could also use iron instead of zinc. And then third, I'm going to use sodium hydroxide. So we're not going to go over the mechanism for the reduction of the nitro group. So don't worry about that mechanism, but just know that if you use zinc or iron with hydrochloric acid followed by sodium hydroxide, that will give you aniline from nitrobenzene. So in the next lecture, we're going to talk about a very specific reaction called Friedel-Crafts alkylation, as well as Friedel-Crafts acylation. And then we'll also talk about a reaction called the Clemmensen reduction. So I will see you in the next video.